tend to close the crack. So when we apply tensile load here, it tends to open the crack. And when we compress it in opposite direction, it tends to close the crack. So for crack growth to occur, it should be generally favorable. Sufficient stress concentration should exist at the crack tip to break bonds, and the crack growth criteria should be fulfilled. Crack growth criteria according to Griffiths, which is energy-based, or global criteria must be fulfilled, or according to English, that stress-based criteria or local criteria should be fulfilled. The stress-based criteria for crack propagation, that is English criteria. So in 1913, English observed the stress concentration around the hole or notch dependent on the radius of curvature of the notch. That means the far field stress sigma naught is amplified near to the hole. Okay, that is sigma max over sigma naught is the stress concentration factor K. Flattened elliptical hole with a sharp tip can be thought of as a crack. So we can see here hole, circular hole, and when we see an elliptical notch, which is considered as a crack. Okay, even the whole circular hole also considered as a crack. So sigma max is equals to sigma naught as a whole plus 1 plus 2 radical of C over rho, which for sharp cracks, that sigma max is approximately equal to 2 times of sigma naught radical C over rho. So what sigma naught is far field stress, and sigma max is stress at hole or crack tip, and rho is hole or crack tip radius, and also C is the crack length or length of the hole or crack, and the K is the stress concentration factor. Stress concentration factor. Okay. So whenever the crack is very sharp, sigma max is equal to 2 times of sigma naught over C. Okay. Sharper the crack, higher the stress concentration. That is so this crack is sharper means we are saying that the radius of crack tip is very small. Rho, crack tip radius rho is very small. More stress amplification or higher value of sigma max will be attained. The circular hole has a stress concentration factor of 3, that is K is equals to 3. From English, okay, that means what? For circular crack, C and rho are equal. That means 1 over C over C, that is 1, radical 1, then it is 2 times of radical 1, gives us 2, 2 plus 1, 3. So we can see it here. Yeah. C over C for circular hole, rho and C are equal. So C over C, we can get this 1, 1 plus 1, 2, 3 times sigma naught. Sigma max equal to 3 times sigma naught. Once we, one way of understanding this formula is if sigma max exceeds sigma t, the theoretical fracture stress, then the material fades by extension of the crack. This is inspired the fact that the applied stress is of much lower magnitude than the theoretical fracture stress. Yeah, so this is for circular hole. For the crack to propagate, the crack tip stress have to do work to break the bonds at the crack tip. This implies that the cohesive energy has to be overcome. If there is no plastic deformation or any other mechanisms of dissipation of energy, the work done appears as the surface energy of the crack surface. Okay, so the fracture stress sigma F, which is the far field of applied stress, can be computed using the approach. Not, so this is sigma cohesive, which is equals to E over pi, and the sigma F is equals to E gamma rho over 4A naught C. So this C is the length of crack. A naught is interatomic spacing, or the distance between center of atoms. This implies the youngest modulus of material, and this is the radius of the crack. Okay. Now, how do the crack tip stress look like? Look, this is the cracked area. So around here there is a crack tip. So 30 millimeter by 10 millimeter size. By zoomed out, okay, we can see here plane stress condition. uh, at the point near to the crack, at the crack tip, there is high stress, that is 8.9, that is high stress concentration. Once we go behind, we can see 3.5 gigapascal, sorry, and then 2 gigapascal and 1 gigapascal. In this region, we can observe 0.5, and this around here 0.2, and go far, it is 0. Here also we can see sigma xx. In the sigma xx also, as a near to crack tip 5.3 gigapascal, then around here 1.5 gigapascal, 0.8, 0.6, 0.4, 0.2, 0.1, and 0. So this is the stress distribution in plane stress condition. So Griffith's criteria for brittle crack propagation. We have noted that the crack length does not appear independently of the crack tip radius in English formula. Intuitively, we can feel that longer crack must be more deleterious. Another point noteworthy in English approach is the implicit assumption that sufficient energy is available in the elastic body to do work to propagate the crack. Okay, so keeping some of these factors in view, Griffiths proposed a condition for crack propagation. Some of the conditions, the first one is bones at the crack tip must be stressed to point of failure, as in English criteria. The amount of strain energy released by the slight unloading of the body due to crack extension must be greater than or equal to surface energy of the crack face created. The second condition, this means the amount of strain energy released must be greater than or equal to surface energy of the crack face created. This implies dUs over dc, the strain energy. This US implies strain energy over dc is a small increment in crack length. Okay, should be greater than or equal to du gamma over dc. This du gamma implies surface energy, or it is energy per unit area, which is surface energy. Essentially, this is like energy balance. The surface energy for the extended crack phase comes from elastically stored energy in a fixed displacement case. Okay. The strain energy released on introduction of very narrow elliptical double-ended crack of the length 2c in infinite plate widths or depths under an uniform stress sigma A is given by the formula reduction in elastic strain is equal to delta U, which is equal to U without crack minus U with crack. So which is equal to US. US is equal to pi C square sigma A square over E. And should be written with negative sign when we reverse the direction, if it is U final minus U initial. Okay. So this is because the body with a crack has lower elastic energy stored in it compared to the body without crack. Also, the assumption is the introduction of the crack does not alter the far field stress. Okay, we can see here what the far field stress. Here, this is load applying. The far field stress are sigma y, which is equal to sigma y, which is equal to sigma a. For now, we assume the stress, this stress arise out of applied displacement are this sigma yy, and this is double-ended through crack, with 2c. Okay, so these are the crack phase. So the unit of US is joule per meter, which is takes the unit of energy. Half crack length is C appears in the formula. E is assumed constant in the process. Sigma is the far field stress. This may result from displacement rather than from the applied force. So the formula for US can be appreciated by considering the energy release from the circular regions of diameter 2c as in the figure. The energy release is which is given elastic energy release from circular region US circular, which is equal to half sigma A square over E times pi c square. That is, this is for the fully circular region. Okay, so the computation of the actual energy release is more involved than is given by the formula. US is equal to pi c square sigma A square over E. So plane stress condition. This is in plane stress condition. Hence, DUC, DUS over DC, which is equal to 2 pi C sigma A square over E. So here, in this case, energy release from the circular region is given by the formula 1 here as above. So that is taken for this region. Okay. For the body in plane strain condition, thickness in z direction into the plane of the page, E is replaced with E over 1 minus mu square. So US is equals to the strain energy, US is